we'll finish the homework so I can comment on W just a little bit. Well, actually, Michel told me that most of you, or a number of you, did the SO3 problem. So I think I regret giving you a hint. I shouldn't have given you a hint. I didn't want that. I wanted you not to solve it. See, and now I have to give you a few harder problems just to make sure. But it's not good if, you know, we need problems that you know, that become too hard at some point. They shouldn't frustrate you, right? Anyway, so the W. You notice that you actually, sorry, that you actually checked. You've seen the discovery of W in this homework, right? Because you've seen the distribution, the angular distribution of electrons, and this is how they saw it. But in order, of course, to get it, they had to polarize it. And there is this irony that it seems impossible. How the hell you're going to polarize a W boson, right, in a machine like PP bar? And you understood, I guess, all of you, right? It was clear in the homework. Quarks are massless. So when they scatter, they actually produce a polarized W. So if I have W polarized like this, and it decays into massless particles, then we know the helicity argument is good, and then we find out the electron cannot go here. W minus. Right? I know immediately. This can't happen. This can happen. So I can get this distribution, right? You don't even have to compute. You got this factor 1 minus cosine theta. Now, plus or minus depends on the convention that you have. Without conventions, it should be 1 minus cosine theta squared, right? Well, what if I say that it's polarized with S theta W? Can we guess that without doing a calculation how it has to be? Can it go up? Can electron go up? And then neutrino goes down.
You cannot.
Cannot. Well, because this is polarized like this. Can it go down?
No.
No, because it's polarized like this. So it's not surprising that you get something proportional to sine theta. If you remember. Okay, that was important to grasp that. Of course, you could think, can electron go here?
In X or something like that.
For example.
Yeah.
And the first glance is, oh, this is strange. How can it go here, right? It's also polarized. Well, the angular momentum, you know, this is quantum mechanics, so you know that it can go there because we don't know what Sx is or Lx. Okay. So I think the W should be clear. It will be. I don't know whether we'll come to it. The next homework is the Z boson. So it's good to see the differences. Okay, the Z boson, when it comes to violation parity, is a little more subtle, but it's basically the same, one and the same calculation. What I want you to see there is really you're counting the number of neutrinos. It's kind of nice.
Is the second problem in this homework another problem that you don't want us to solve?
No.
This you want us to solve?
Yes. That's really easy.
It is easy. Okay.
It's easy, it looks hard, but after a while, I think it's, well, I don't know. It's easy to say that something is easy when you forgot how you know, it's been with me, I don't know, first time, when maybe it's not, I'm not sure. I can't judge anymore.
What do you mean that you don't want us to solve?
No, that it's really hard. You know, said I had to give you problems, I guess this is what he was alluding to. Hoping, you know, that's really hard. No, this should be fairly straightforward. You have to write the mass matrix. You can always write the general mass matrix. It depends on the general generators. And then you have to look for the eigenvalue 0 of that mass matrix. And I didn't say find the eigenstate with the mass. I actually gave it to you, so it's a little easier. I could have said find the photon. That would have been hard, because then how to think about it, it's not easy. So, well. maybe enough for hints. So what did we, let's try to summarize what we've learned. There were two pieces of the Lagrange, but we could write it again, okay? So we go on more, continue with the standard model. The terms well, I guess everything is equal importance, so let's write it down. So I have my fermionic kinetic energy. We can write like this. I should, strictly speaking, separate left and right, but I don't have to if I specify you the action of the generators. Then you can do it yourselves, you agree? So we could write kinetic energies. Then there is the Higgs kinetic energy. Then there are gauge boson kinetic energies. Here there is something maybe to talk about here. We'll come back to this. It is interesting. There is a Young-Mills interaction which turns out to be important. And then the U1 piece. And a few interactions. Well, actually here the interactions are hidden. So d mu for us is d mu minus ig pa a mu a minus ig prime y over 2 mu. And then I have minus Yukawa and the potential. And the potential is the good old Mexican head generalized sort of. And the Yukawa is of the type QL, Yukawa down, phi, dr, and so on for other species. Which led to, when the dust settles, to fermion masses plus the Yukawa interaction of the Higgs. Higgs is a scalar, spin 0, even parity, so it couples to a bar F. There are pseudoscalars that here don't exist, right? We sort of eat them, W and Z. So we are left with the very simple Yukawa interaction. And from here, we had it was G and W, W plus W minus, plus 1/2 G over cosine theta W, mz, z squared. As usual, Higgs couples to the masses and appropriate couplings. And we had an important relation that mz cosine theta W, the fundamental relation of the there is also a relation between MW and V, but it's not so crucial. That's the definition of V, if you wish. Okay, I'm not writing the potential, so let's not worry about that. So it's very simple, very sort of, it's a sort of, all of it is photon-like interaction. There is no flavor change, as we say. Well, there cannot be flavor change because I'm pretending there is one generation, so the question that you wanted to know is what happens when I have more generations. By the way, there is this interesting thing that the fact that there are more generations to some people is a deep question. I sort of oscillate on that. Sometimes I also felt it's a question, but how do you answer a question? You know, why there are 3 generations? You say, oh, I want to think about this deep question. If there was 1 generation, I go ask you why there is just 1 generation. Isn't that strange that there is just 1 generation? Why should nature just make 1 piece of something? So there is a danger when you ask a fundamental question that you don't answer it, but you cheat on yourself. So you say there are 3 generations. Aha. So maybe there is some family symmetry. Generation symmetry that unifies them. So what symmetry should I take? Then you take SU3. But you're taking SU3 because there are 3 families. So you think you're answering a question that you are not answering the question, you're doing opposite from that. You're using that as an input. Well, there was this famous, Isidore Rabi asked a question. Who ordered that when they found the muon?
But the decay of Z goes on. Does it indicate that there are only 3 neutrinos? Then why do we ask the question that there are more generations than 3?
But if there are 4, you would ask why there are 4. What question you ask when you ask me why there are 3?
No, I'm saying that the analysis of that decay, does it indicate that there are only 3 neutrinos?
Well, it's more than that. No, it doesn't. I'll talk about it now. No, it doesn't. That's a question in the homework. No, the homework says...
See, Dr. Smirnov told us that the invisible...
He was wrong.
Okay.
If he said that.
He said that the invisible mode of that decay told that there are 3 neutrinos.
No, it was even in your times. I don't know why he shouldn't have said that. But I want you to do the homework and then we talk about it. You see the question at the end of the homework. No, this is not true. Even in your times, it was said at the time that it was a proof that there are 3 generations. That's if there are 3 neutrinos, that's a proof that there are 3 neutrinos. As usual, there are always loopholes when you claim that. Well, there is a hint in the answer to the homework question is what I'm saying now. Well, you have to think about it. When I come back, I'm away next week, so when I come back, we'll have ample time to summarize. We can talk a little bit then about the high precision W and Z physics once you do the homework. But even that who have just told me that there are 3 generations, if this was true, let's not answer the question why there are 3 generations. No, we know that there are 3 generations because otherwise we would have seen the 4th generation. LHC has enough energy, and you will see. I will show you what I mean by that. But let's go step by step. So, well, when you ask, if there is 2 generations, you get a beautiful flavor physics, kaon physics. It's a wonderful thing which has to do with kaon oscillating into kaon bar. You get things which are you get equivalation. You need 3 generations. Okay, so that by itself could be an answer. In a sense, the beauty of the physical phenomena that you're describing could be an answer. I don't know. But so let's do for the moment, let's talk about 2 generations. So I'll generalize it easily. Well, I'll be kind of doing 2 and n at the same time. So you tell me that there are more generations. What should I do? What do I have to change here? By incorporating more generation. Which piece of the Lagrangian? Let's go back. This is independent. You agree? This is not to do with generations. This is okay. This is okay. I will write my Yukawa interaction. I should have more generations, okay. And then there are more generations. I don't know a priori if the particles are physical. That I write the particle in me Lagrangian, the states they introduce. Right? When there is more of the same species, the physical state could be a mixture of them. The physical state is a eigenstate of spin, whatever, and charge and so on, by that of mass. So there is no reason why 2 states which are exactly the same cannot mix and produce orthogonal combinations. An example here is A3 and B. A3 and B, notice, have the same charge, have everything that matters. They have the same charge, right? Q is 0. Of course, they have SU2 charges which are different, but SU2 is broken. So they can mix now. And they do mix. Out of this, I produce this thing which is a photon, right? A3 and so on. And the Z orthogonal, maybe not right. So it can happen also in the case of fermions. So in other words, I should have a notation. So let me say the notation should be this to start with. I don't know a better one. Just to notice that they are, we call them weak eigenstates, Lagrangian eigenstates. The eigenstates of weak interaction, but not necessarily eigenstates of mass. Okay, I'm anticipating.
Can you say that they have a definite flavor?
No, because notice when I write down my Yukawa interaction. Okay, so let's write it. Let's start with down quarks. So I'll have QL0, Yukawa D. Now this is a matrix, you agree. If there is more generations, well, I'll be clear. Phi dr. Remember, I can just take one species because it just repeats. What I mean by this is QL0 I, Yukawa down Ij, phi dr 0j. Ij is 1 to n. So notice at this point they don't even have mass. So this point doesn't even make no sense who the particle is. Any linear combination of any state I take, or a group of states, is as good as the one I started with. So they cannot have fixed flavor. It doesn't make sense to talk of flavor at this point. Flavor is defined once you identify. So if you are completely the same, you have to identify the difference between you and me to then talk of Hassan and Boran. Imagine twin, everything the same. We have to find one difference.
Don't they have different
And that's a mess.
Don't they have different couplings even in the before symmetry breaking? That would be like one way to identify them.
Right, but they don't because they define, remember they define through their gauge interaction.
Yeah.
In other words, I define them like this. So let's see what I mean by this. There is UD 0, CS 0. I'm calling them. I'm actually not saying. I'm saying that there is an index I. I shouldn't. I'm giving them a name. You see, I'm cheating here. I shouldn't do this. But sometimes we actually do that, which is sort of not telling you anything. This is not really a, you understand what I'm saying? Or really what I should have put here in an index I. And therefore, and once I say that they have the same quantum numbers, I just say the couplings are the same. I don't have to say anything else. Of course, I'm saying that dr I0. When I write like this, I'm assuming that they have the same hypercharge. I'm tacitly assuming, of course, that they have the same hypercharge. I'm assuming that they have the same hypercharge because I know that they have the same hypercharge. Nature tells me, it's not that I am predicting it. Here, I'm using the fact of nature. Here, I'm actually saying more. Once I have a principle, which is a group theory, that of course tells me everything is decided when I write like this. But here, not. They could have arbitrary different charges. So I'm assuming here that they are all of the types of down quark. Later on, because I've seen that they come like that. Then, of course, they have the same one and the same covariant derivative. Once they have the same covariant derivative, they have the same coupling, so I can't distinguish them. That's what I meant.
Yes, I was talking about the Yukawa coupling, but okay, in this case it's only with the quantum numbers.
Well, they have different, there is a matrix of numbers. I can't even have a state here which is an identifier. In general, there is no reason that I should couple to I, because they have the same quantum numbers.
No?
True. So I don't even have states, physical
Yeah,
states.
I see.
Right. I don't know what I have at this point. What I have to do
Break.
in order to start
Very good.
Break.
and identify
The masses.
the
So,
masses.
I guess.
This is what I've done here. Here it was easy. Here the group structure of the standard model dictated in my eigenstates. I didn't have to do anything. This came out. Remember, this was predicted. By choosing it, it was here. Of course, you know, there is an educated guess here. Nothing is magic. It's not, you know, a pigeon turning into a handkerchief.
It's the other way around.
It's almost the other way around, right? Because you will see when you build, you know, you should do for fun, build a model of something. Then you will see, I have to think, but what Higgs should I choose? So you look for the Higgs that can reproduce the world in which you and I live. The beauty is that once you made some simple thing, you know, you had your principle, a lot of information will follow. So then you will be surprised when you're on the right track. The great thing about great theories of nature that they bring in things you have never imagined. Because even Einstein, even the greatest works were done, what all that he wanted to reproduce, Newton, it was just then applied to the particle states that can move fast in a strong field. And he came up with a certain principle, okay? The principle that comes in was done in order to reproduce the world. The beauty is that then you get predictions. So I do get the predictions by doing that. I never expected this. And I would not have guessed that everything will work out. But I had to start with a doublet. Why? To couple it here. So partly it's sort of guess, partly is a trick, and partly is a genuine new phenomenon. So when phi, of course, I always write phi. Let's have it and try not to erase it. This is my phi. I mean my unitary gauge. I don't want to do loops, I just want to understand what the physics is. So when I do that, what I get from here is 1 over square root of 2 dl 0 Yukawa down dr 0 v plus h. This is a matrix now. Okay, you understand? Right? There is a hidden index here. So this is a matrix. Notice a beautiful prediction, the first one. And this is a miracle of the minimal standard model, okay? I'll show you what happens if you try to modify the theory a little bit. You can actually have a nice homework that you could learn a lot. Notice, when I diagonalize Yukawa coupling, masses, okay, maybe I can be even more specific here. So I have 1 over square root of 2, I can write it nicer, I can write dl0 bar md dr0. md is what? It's Yukawa d times v. No square root of 2. Okay. The Higgs couples, I can write immediately like this. What I have to do, of course, I have to diagonalize this matrix, okay? This is that I was lucky when I did the A3 and B, it happened by itself. Okay, it's not so lucky, but I can diagonalize the matrix, it's not a big deal. Notice when I diagonalize M, I will diagonalize the Higgs interaction. Higgs goes with the same structure. You can see it here. So M becoming diagonal implies Yukawa, and this will be true for any species, becoming diagonal. we'll get the same simple, beautiful, flavor-conserving interaction. This, what I wrote, is true. I didn't know it was going to be true. I pretended there is one generation, but actually it doesn't matter. I may have 155 generations. Who cares? Once I diagonalize it, what I mean by diagonalizing, I'm going to write this thing. I'm going to write this as dl bar md dr. md here. This is the problem with the notation. It's a diagonal matrix. Sometimes down stands for down quark, and sometimes down stands for all down quarks. Otherwise, I could draw some other, but I don't want to do that. MD, MS, MB, and whatever. You tell me how many generations there are.
So this means that if there exist more generations, we cannot have any idea of what is the mass scale of the new generations. Because they are independent and not mixed by kids.
Well, even before new generations, how can I've never managed to, never before in the history I could tell anything about the past. Kepler tried. Kepler wanted to calculate the masses of planets. The distances, sorry, not the masses. Well, similar thing. He failed. So that he can tell you if you find the next planet, it's going to be there. It's not like you're asking a question that somehow before people wouldn't even ask. It became a household question that apparently every Dick and Harry should answer. So every day I have to turn on archive and see that hundreds of people are writing an answer to one of the deepest questions in human understanding. It's true that sometimes I get a correlation. It's true. You can say here, but here you got a correlation. True. It's a little miracle. By the way, in order to do anything with this, there is really no prediction here because I don't know what theta W is. I had to measure it. I had no idea. I couldn't tell you what the Z is. Then I went to measure this, and I needed different processes, not from here. So it's not that the Z mass was predicted. It was related to some interaction. So in a few minutes you can ask me, or I will try to readdress this issue, maybe in a little different context. But yes, I agree with you. I don't know I never knew what the mass of the strange quark would be. Of course, when you have some existing, okay, sorry. Let's come back to this question 10 minutes from now. Let's try to make it more physical. In other words, even if I don't predict the mass, let's try to relate it to something else. That, of course, we may achieve.
For example, the Jim mechanism tells the mass of charm quark.
Charm quark turns out to be related to a physical process. This is very interesting, okay, because masses enter somewhere. Well, actually, it gets related to the mixing. Mixing I mentioned before. It's not okay. We'll discuss the meaning of what you've studied already with Smirnov. Well, first I want you to appreciate that once I diagonalize these masses, I've diagonalized the Higgs interaction. Okay. So my Higgs interaction in the end has to look like this in the physical basis. I'm changing the basis now. So what I'm doing, let's write it here. I'm actually saying, well, it's done here. So let's introduce some notation. Let's say that then MD is U D MD VD dagger. That's what I mean. If this basic, I don't know anything about them. If it was Hermitian, U would be equal to V. But since it's not Hermitian, I don't want to assume that left and right. And I'm never sure about the notation. What is a good notation? We could, well, let's try this. It requires more writing, but it's useful to be specific. I don't even have to put the dagger here. I don't know why I'm doing it. I got used to it. It's an arbitrary matrix, so who cares? I call it dagger. Now, to get the meaning of this, notice that MD dagger is, what is it? URD, MD, UL, D dagger. I'm assuming that MD is real. I'm assuming that I can break any matrix into this form where these are real. Actually, I'm positive, these are masses, which I will define a real, a positive answer. And you will see that it makes sense immediately. To get the meaning of this, so notice that MD dagger is what? Is ULD, MD square, ULD dagger. This is a Hermitian matrix. So now I understand the meaning. What is UL? It's whatever diagonalizes. This you've done all your life, since you were little. You know how to diagonalize Hermitian matrices. You can tell me, you can find the eigenstates and eigenvalues, which are hidden here. And of course, this is real and positive. A Hermitian matrix has elements which are real and positive. Notice with this conversion, still the sign is not clear. But I fix the sign by the overall VR. It's a phase that I can always, the sign of the Fermion mass is not physical. Not even the phase, but surely not the mine. And what is UR? Well, look at the other Hermitian matrix, MD dagger MD. This is URD, MD square, URD dagger. So you understand this is possible, this has a physical meaning, these are Hermitian matrices, so it tells me that it's okay what I wrote, it fits what I know about the Hermitian matrix is okay. And generally I don't want to assume that they are the same, because these matrices do not have to be the same. Right, this is Hermitian, obviously. Which means, what it means that, what does it mean? That well, I'll start it from here, I don't need this. What it means that DL0 bar, ULD, MD, URD dagger, DR0 is DL bar MD DR. Right? That's my definition of new states. These are physical states. So the zero subscript denotes weak, what we say, eigenstates or states. These are the states that give me diagonal weak interaction. I started with something which is diagonal, okay? And these are physical or mass. This is what we mean by eigenstates. Everything else was fixed anyway. And so I can read it off here, right? What do I have? That from here, DL R is what? UL R dagger DL R0. I know how to go from one basis to another. I go from one basis to another, so the matrix is the diagonal mass matrix. So see, before they had a mass, there was no sense of talking about flavor. Notice, if they have the same mass, imagine that they all have the same mass. Again, there'd be no sense of talking about flavor, because how will I distinguish them? There is no down charm, a strange quark. So I'm assuming that they don't have the same mass. Well, this is true. Now you see the mixing. So these ugly mixings, okay, there is a mess. Now the standard model starts to lose some of its beauty. The simplicity, the elegance. I don't mean the physical beauty, I mean the mathematical beauty. There is both that you and I appreciate. And probably mathematical more than physical. At least some of you from you told me, and I know that your age, I think I appreciate it much more mathematical. Now maybe I'm a little more balanced. But still, you know, there is a beauty of a simple formula. So here, fortunately, I'm okay. I have this nice, elegant interaction. What about the photon interactions, which I didn't write from here? I had an interaction like this, which would be FL0 gamma mu FL0. Well, let me write Q FL0 plus FR0 gamma mu Q FR0 times A mu. I have separated left and right, you agree? Why am I separating them now? I never did it before. Because they rotate differently in general. So I need to speak now left and right separately. I have no right anymore. When there was one generation, there was nothing to worry about because there was no mixing. And left and right fermions have the same charge. So what's going to happen to the mixing? Can you tell me? Is there a mixing or there is no mixing? By the way, I can generalize this, what I wrote here, immediately. Let me generalize it. That this is true for every species. FLR is ULF. So there is a D index here also. You see this? There are too many bloody index. LF, LR, F, dagger, F, L, right, 0. The same will be for the electron, for the up quark, and so on, okay? It comes from one and the same Yukawa interaction with Boris-Down. We check that. So is the mixing going to stay or not? Can you tell me quickly? It goes away. Why? Because I will write this as a FL bar. So FL0 is the opposite, is UL. So I will get UFL dagger, UFL, gamma mu, FL. And the same for R. Sorry, there is Q hidden. They have the same charge. So Q is just a number. I get on the left dagger, on the right, and this is 1. So the beauty is coming back. Okay, it's not that bad as I was worried. If I get this mixing, you know, well, it couldn't have happened, okay? We would have failed because we know that it's not what the photon like to do. Photon will never take an electron into a muon. Never. And the standard model says it can never happen. This is the structure. The structure, once I, you know, started to do what I started to do, certain things are emerging, so this structure is being predicted. Well, predicted. Hidden inside is the fact that these particles have the same charge, that they have universal coupling. These are really repetitions of families. But that's okay, I wrote them. I wrote them structurally here. And erased. So we did a structure, that's a prediction. So I don't have to worry. The Z boson interaction will be the same. Of course, there is no difference. It's just Z has T3 minus Q, but it's the same. You've done this with me now, I'm sure. No? What? This? You didn't? Because I'm sure that he have talked about flavor mixing.
Yeah, he talked about flavor mixing.
If he talked about flavor mixing, he must have shown you this, or you should have asked him.
Well, he talked a little bit about the fact that you have to introduce another U1 and one of them will become Z and one of them will become photon after mixing, but he didn't.
Right. Well, it doesn't matter. All that he knew, it doesn't matter how you would do it. What he knew, what he knows, He knows what all of us know that whatever we know, whatever we don't know, that this guy have the same charge. Okay, this is the thing is that the families are really Xerox copies of each other. Once they have the same charge, this is just a number that I can take out. So therefore, this goes through. If they had a little different charges, then I will introduce the mixing. So it's very important that they have the same charge. Okay, so photon and Z cannot have any mixing, just the way it disappears from the Higgs. You see what happens at a neutral interaction that we say, the mixing disappears because you get U dagger U. That happened in the Yokogawa interaction. I could have guessed that. Where will the mixing go? Because there is mixing, fortunately. And because of this mixing, beautiful things can happen. We have all this interesting flavor physics. It doesn't go into the photon, it doesn't go into the Z, into the Higgs, so where can it go? W. Why does it go into the W? Because W looks like this. G over square root of 2, it looks like this. I can write it in this U0 bar, C0 bar, T0 bar. I should put the index 1, 2, 3 really, because, but anyway, subscript 0 tells me there are no physical states. Gamma mu, D0, S0, B0, left, left, W mu plus. Right, this is a W interaction. So there is a fortunate thing that in all this mess, basically all that we wrote for one generation, most of the time, you can just predict there is one generation. Unless you're worried what happens when one turns into another, just think of one generation. If you want to understand, flavor mixing, think of 2 generations, not of 3, because the formulas are simple and you can see it's more picturesque. And this becomes G over square root of 2. This should be U bar, C bar, T bar, U up, L dagger. Agreed? I'm rotating the up quarks. I should rotate the down quarks, so I'll get U dl. And what we are saying, since the masses of up and down quarks are completely different from each other, there would be a miracle that this was one and the same matrix. There is nothing that they have in common. Therefore, we are saying we don't want to imply that this is, we got a general matrix, and we call this matrix Cabibbo rotation. And if you want more, you call it Km. And you could say if you put the 4th generation, you can address the same name, okay. It's almost trivial. Km becomes important, we'll see why. Why the name is important. It's kind of trivial what Km did. They just said there is one more generation, okay, everything was there, but they found out that there could be a CP phase that we'll talk about. So in other words, in order to get the CP phase, they predicted the existence of new particles. That's beautiful. Except that what they imitate is the work of Jim. Now, Jim never got a Nobel Prize. It's worse. Zweig never got a Nobel Prize, the father of quarks. That's crazy. You got a Nobel Prize for fixing 6 quarks, but the actually profound suggestion, discovery, the theory of quarks, written by Zweig. Gell-Mann to some degree, Zweig much more seriously. We don't talk so much about Zweig because he didn't call them quarks. Quarks is a catchy name, especially if you like James Joyce. Gell-Mann likes James Joyce. I don't like James Joyce. It's a terrible thing to say in Trieste. I tried to like him, even before coming here. Just doesn't write for me. But 3 quarks for Mr. Marx, says Finnegan's Wake. He called them aces. That's why. what to say here. What should you already know a lot, of course, we know, but maybe I should remind you. So when the dust settles, it's not so bad. We can forget everything, just one generation, except there is a little mixing here. Notice that the only thing you can probe is this difference, okay? It doesn't make sense. People often say that they would like to understand, they want to have a theory of mixings, because you are asking, now you can ask a little less deep question. You are saying you have a M up, M charm, M top, okay, I didn't predict them, M down, M strange, M bottom. And then I have three mixing angles, theta 1, theta 2, theta 3, and there is a CP phase. Only one phase. I remind you why one phase is strange. You would expect many more phases. You say, aha, what I can do, maybe I cannot compute the masses, but maybe I can relate the mixing angles to the masses. Now, how can I do that? That's a tricky thing. Remember what the mixing angles come from. So to remind you once again, VCKM is this thing. These are the things that diagonalize the up and down mass matrices. So in other words, M up, M fermion, once again, is UL fermion, M fermion, U right fermion dagger. I think I wrote like this. You're saying, aha. I don't like this research very much, okay? I've sometimes done it. I've written a paper on this. I don't think it's, actually even how to get a phase. It was maybe one of the first papers with Ravi Mohapatra. You are saying, Well, you see the tricky thing. All I know is this, but now you can say, if I have a form of the mass matrix, some nice form of the mass matrix, for example, if mass matrices are symmetric, then it's easier to find the mixing angles. Let's imagine two generations. Why? Because you know the symmetric mass matrix. Write the symmetric mass matrix. You know the mixing angle here? This you should know in your sleep, like Pauli matrices. This is very important because very often you find this. 1/2, it goes with a half tangent to theta. So when the mixing is small, it's just theta. It's equal to what?
Theta by 2. Sorry, theta. Yeah. If theta is small, then.
No, but what is it in the matrix?
Oh, okay.
In this matrix, what will be? Well, it has to be proportional to C. If there is C0, there is no mixing. And it turns out it goes like this. It tells you, well, whatever it tells you. So you say the following, okay? This is just to make Victor happy. Maybe some of you others, okay? But just to show you what people try to do. And by the way, this is what Weinberg did. The first paper was written by Weinberg. And I got very excited. I thought it was beautiful. Now I don't think anymore. So it would be much nicer if it was 0. Because if it is 0, then I have very nice, I immediately know what the mixing is. But you see, I live in the world in which second generation is much heavier than the first generation. Right? So what are the eigenvalues of this matrix, can you tell me? If B is much bigger than C, so this is my mass matrix, let's say mass of down quarks. I'm looking at the mass of the down quarks, it has this form. So this is a down quark mixing. Okay? Try to pay attention to this, a little digression, okay? You don't have to know that, we are not standing in the standard model, but if you can stay with me for 5 minutes. If B is much bigger than C, can you tell me quickly what the eigenvalues are?
0 and B.
Sorry?
0 and B.
No.
Because
Determinant is not 0.
well, the quality coin that becomes is.
I'm not saying that Z is 0, it's just bigger. No, I want to keep Z.
Oh, okay.
No, because down quark has a mass. I can't go into the approximation of M down going to 0. It's still relevant, okay? I will tell you why M down quark is relevant when we talk about the quark masses, okay? It's not 0. If down quark had a mass 0 and up quark, pion would be massless. There's a beautiful thing actually. Pion is a kind of Goldstone boson almost. This is how it all started with the work on Nambu, but today it's not what you want to learn. So then, tell me, by the way, this is a famous matrix today, it's called the seesaw matrix. You will be running into it, you will be hearing a lot about it. But it's sort of, people talk about it neutrinos, but it's not a big deal, it's a trivial thing, this matrix. Okay. Maybe Victor, you have one to say?
CV and C over B.
C square over B square and 2 B plus C square over B square.
No, C.
B is much bigger.
Then
So you can say that one eigenvalue, let's call it M strange, is roughly MB, you agree? Is B.
Yeah.
Plus a small correction. I don't have to write the small correction because it's small.
Yes, the other
Yeah,
is 2
yes.
C over.
It's true that there is a correction, no, but let me not write it, okay, plus. And then the light mass
Over B square.
is C square over
No, over B.
over B. With a sign, there is a, but the sign of the mass doesn't matter actually. There is strictly speaking a minus sign. How do I know that? Because determinant is minus C squared. Determinant is the product, so how do you know? The trace is the sum, but C is small, so the trace. So from here I find that the trace of MD is roughly B. That's okay. C is very small, I'm saying. And determinant of MD is minus C squared, because determinant is the product.
Well, what do you mean when you say that a trace of MD is roughly B?
Yes, exactly.
Sorry?
You said the trace of MD is roughly B. But
Right, because there is B minus C squared over B.
But the trace is B.
Right, but these are approximate eigenstates. Because this is not an eigenstate, the eigenvalue. There is also a plus C squared over B probably.
I'm just talking about that matrix.
Right,
This matrix.
me too.
The trace is B because the
Yeah, sure. But, right, the trace will work out because MS is not just B. There is a correction here if you do it correct.
But the trace is just the sum of the diagonal matrix. Diagonal.
True. Sum this, you will get B. I just added something because I said that C is very small. I'm finding approximate eigenvalues. If you do exact eigenvalues, you will get something like this. Something. I don't want to do it here even. The formula is more complicated, by the way. We can write the eigenvalues. All I'm saying in a small approximation, it's got to be like this. Why? Because the trace sums correctly, and now the determinant is not fitting, but because I'm neglecting the term which is of the order of C to the 4th. Depends what I want to keep. If I want to keep C squared, I will write like this. Agree? And then even the determinant is correct, because this times this will give me minus C squared. This will be 0. I'm going to neglect. But this is small. When you have a large element, you don't keep the small element, okay? This is what I was trying to say. You keep it here because this is not small compared to 0. Okay? C squared over B is very small compared to B. But it's not small compared to 0. I have to keep it here.
So you are just retaining the first non-vanishing term in C in both of the cases.
We'll be talking a lot about C, so I don't know. Can you maybe you could have while I was talking you could have found the eigenvalue. This is quadratic equation. So what will be the eigenvalue would be minus B plus the square root of B squared minus 4C, something like this, or 2, I don't know. No, something like this.
It will be
No,
plus 4C.
it's plus 4C squared.
Yeah.
Okay, if you say so.
And actually we had a whole
whatever. And then we just expand them.
yeah.
And the eigenvalues are whatever they are. Here, you know, the logic is what you do. When you're perturbing 0, then you keep small. When you're perturbing a large number, then you don't keep small. Okay, what I'm saying. I couldn't have been wrong because I made an estimate of the roughly about the size, right? Do you agree? Oops. So let's not keep this. Let's keep this. So now what you're saying, you can tell me, look, I can do the following. What is this now? Up to the sign. I will change the sign because I can just change the right-handed field, right? The sign of the Fermi mass is not physical. What is it?
MD over MS square root.
M?
MD over MS.
Square, I think. No, square root.
Square root, yeah.
Very good. Great. So notice, this is small. So I'm getting the theta is roughly, theta down is roughly a square root of MD minus MS over MS. I have to do the same thing for the up-walk matrix. Imagine I assume the same form of the up-walk matrix. I will get this. Agree? Roughly. But what is Cabibbo angle?
0.22.
What is the Kobayashi-Maskawa-Cabibbo matrix, or Cabibbo matrix in this case? It's U up dagger UD. So in other words, theta Cabibbo is the difference between these two, up to a sign, I don't care. Right? Rotation and anti-rotation. So you could say that you predict, I'm giving an example, that theta Cabibbo is roughly ND over MS. Because this is very small. Charm is very heavy. Compared to the strange quark, charm is very heavy. It's 10 times heavier. More than 10 times heavier. And actually, the up quark is lighter than the down quark. Even there is a factor of 2. It seems to be so. So you are saying, by the way, this works very nice. Put the numbers and you will see that you get a nice, so you get excited. So now you do the following. Look what we did. You said, I know what the mixing angle is. I want to have a theory of the mixing angle, you said. I'm trying to give you an example of how you would try to answer this great fundamental question. I couldn't predict the mass, but maybe I could relate masses to mixings. So what I did, I don't know, I have no idea what to do. I started to guess the form of the mass matrix. You know, first I took it symmetric. Why in the world did I take it symmetric? Then I took a 0 here. Then I got a nice result. Now I go and scratch my head, said, oh, I'll make a prediction now. I'm going to assume this mass matrix. Then I'll get that thing. But it's sort of, that's not what we did. We actually went the other way around. So imagine if I now claim, why we didn't write the paper, he said in his talk. Let's give him credit for that. A lot of people have been writing papers ever since. Thousands of papers have been written. And then as I'm speaking here, someone is clicking on the archive, maybe sending yet another paper. Now, notice that this by itself is completely useless because you can never probe it. These are words. The only thing that you can probe is this. In other words, you and I cannot probe the form of the mass matrices. Now, of course, the next step is, you don't want to just say that you dreamt this mass matrix, that people wouldn't publish for you. You can say, my friend told me, my mother told me, that also wouldn't be publishable. So you say, I will now see if this matrix has more symmetry. If it has more symmetry, I will postulate that symmetry. It's not doing research. This maybe is doing search. You know, there's a nice, in English, you know, research is a nice word. It's not just reaching. You should reflect on that. You should think about what you're doing, okay? But here we are cheating ourselves. We are eating our tails. First, I'm not predicting it because I went this way. In a sense, it's becoming a tautology when you do that. It's like, suppose I ask you, you know, proton lives a long time. Why does proton live a long time? I am a deep philosopher of science, so I ask you, and you are also deep. Okay. And you tell me because baryon number is conserved. That's not an answer. Okay. That's worse than answering. It's just really tautology, and actually bad tautology, because it's a fundamental thing that proton is stable. If proton decays, baryon number will be violating. We have no problem with that. So you can't use it as a logic, but here it's worse because I cannot probe this. You can ask this question in a theory that is not just sensitive to this, but to the form of the mass matrix itself. In other words, I need to have a theory which would measure this, because the form of the mass matrix dictates if I know the mass matrix, and somehow I got it, I have something fundamental, some beautiful symmetry, I got the mass matrix. That means I can predict these. In order to test my idea, I should be able to measure them. There are theories, they're called grand unification. So it's fun to work on that, then you have to go beyond the standard model, and you can actually address that question. You will see it's hard to get information there. What you can try to get in the grand unification, in grand unification you unify quarks and leptons. You can do a more modern thing. You say, I can't predict quarks or leptons, but maybe I can find some correlation. That in principle has been done. Why? Because there are new interactions in grand unification which are sensitive to this. But in the standard model, I want you to know, when you just add additional symmetries, there is no even way of addressing the question. It's a bad question. Worrying about sizes, you see, it's the analogy I will give it, it's a little vulgar but simple, okay? At least I have an experience and I have some theory about the human size. So if someone is entering, a human being is entering a door, I can guess the size of that person, roughly. But not if it's an animal, because it could be a giraffe or an ant, and I could be off by orders of magnitude. So within the framework that I know one thing, I cannot go beyond, okay? I just want to tell you. So in the standard model, I took some time, maybe more than it was necessary, but I want you to appreciate that. Now in the standard model, this question is forbidden. It's a bad question, and you know, because we cannot measure it, we can write, continuously keep writing papers, imagining another form of the mass matrix that will give you a good mixing angle, you know, just keep playing. But there will be no way of testing. So, not even wrong would probably. All these song and dance for you to appreciate in the standard model. We'll come back to the seesaw matrix, so if you remember some of it, it will be useful. If not important, we'll do it more seriously. In the standard model, unfortunately, all I can do is sort of characterize this. But I can't make predictions. That's okay, I can still make correlations, as we'll do in a second. The first thing is, it's unitary, you agree? Because these are unitary matrices. I diagonalize matrices by unitary matrices. Hermitian the same. General different. Unitary matrices has angles and phases. How many angles? How do you define the angle? How do I separate angle from phase?
You have one angle for rotation about one axis.
Right, but how does it define? In other words, when this is real, then I talk of angles. So the rest, then I call phases. So this is n times n matrix. How many angles? Rotations. These are now rotations, orthogonal matrices.
Yes, n minus 1.
N n minus 1, thank you.
1 to
1 half n n minus 1. The number of generators of the orthogonal matrix, okay. 3 Euler angles in SO3. So how many phases?
N square minus
n plus 1. It has to, because I have n square elements. So it's a mess. I have a lot of phases, it seems. For example, in 2 times 2 case with 2 generations, I have how many phases? So let's first take two generations. N is equal to 1 angle. It's called theta cavivo. How many phases? 3 phases. So how come Cavivo didn't write this?
You can rephase.
Assuming he was not completely stupid.
The definition in the course or in the
Phases are not. Why? What we've done up to now, we went from Q0 M Q0 into Q bar MQ at the end. And I can still, actually there was left, right, left, right. I can still change the phase that I have on the right-handed rotation by changing the phase of the right-handed rotation. I have a freedom. This is very important, and the freedom exists because right-handed particles do not interact with W. So as long, I've diagonalized this, and I don't want to keep that. I make this positive. I fix my basis. This is positive number. I can still keep it positive if I change QL bar e to the minus E alpha and QR e to the I alpha. Nothing happens as long I can keep making rotations. I diagonalize, but I can still keep rotating phase-wise, not angles anymore. Okay? As long as I do the same rotation on left and right. But I can always do that because nobody knows about my right-handed. They are phantom particles. W doesn't know they exist even. So how many phases I can choose? I have how many quarks? 4 n generations? 2n. Well, what did I spoke of? No, I should have been a little more careful. I meant, correct, no, I said correctly, n generations. I was clear, sorry. N generations. 2n flavors, 2n states. So that means that I have 2n arbitrary phases that I can redefine.
But only the relative phases matter. Yes.
Well, which relative phases matter?
You can set 1 to 0 and then
Why?
Overall phase in the whole of
the absolute phases are not.
Well, I don't know. I can't do it. If I knew the form of this, I couldn't do it. Okay, I guess you are telling me it's almost, this is left, sorry, this is left. It's almost true what you're saying. Or maybe it's true, maybe you understand it. Well, let's try to see. I can write like this. Up, going e to the I, alpha up, up. Charm goes, let me write like this. Alpha charm, charm. Top goes e into the I, alpha top, top. I start changing these phases. D goes into e to the I, alpha d, d, and so on. Now let me leave some space here. This I can write as e to the I, alpha u e to the I alpha c minus alpha u c. Let me do something stupid. E to the I alpha u, e to the I alpha t minus alpha u t. I can always write like that. Then I can say that d goes into e to the I alpha u, e to the I alpha d minus alpha u, d. And so on. I took this phase out. Now it's true what you said. I've taken this phase as a common phase. And here also. For strange and bottom. And of course, if ECKM measures the relative thing, it's always the difference it measures, of angles of phases, right? So remember the thing, Cabibbo angle doesn't care what is up mixing or down mixing. You can be in a basis. Do you assume down quarks are diagonal? You can work in that basis. Then up quark mass matrix is rotated by charm. Or you can say, oh, I don't like that, you know. Yase and Zakaria working. No, I prefer that up quark, you know, whatever. It's up to you. That's free. So actually there is 2n minus 1 phases, it turns out. It's a nice subtlety, which tells me that the number of physical phases, so number of phases. By the way, did you do the calculation? You should convince yourself, you should do 2 generations and get rid of the phase, of all the phases, right? And you know, one thing is to count, the other is to see explicitly. Sometimes it's fun. So the number of phases is 1/2 nn plus 1 minus 2n minus 1. Not 2n, I would have been wrong if Hassan hadn't corrected me. 1/2. So what do I get? I get n squared plus n. This time I have to multiply by 2, so that's minus 4n plus 2, right? Which is 1/2. I notice this is minus 3n, so it's plus 2 is this. No, maybe better like this. I want to get 3n plus 2, minus 3n plus 2. That's the number of phases. This is the famous result of Kobayashi and Mascava, a fundamental thing that tells us that you need a 3rd generation.
Well, actually, in particle physics course, we had a homework question to derive
About this.
Oh. So I didn't have to do this, I could have just cited it.
It's good.
It's good to remember, you know, things pass. So this repetition, you could say, is it necessary to have 2 courses like this? I think it's good. You and I know it, you know, we keep forgetting. So there are 2 ways not to forget. One is you work it out, then you tend to remember, but even then with time, there are a lot of homeworks. It's interesting, this level of forgetting. When I studied, I forgot. The things that I would just do like a homework, I forgot. But the thing that you do like research, when you're really coming up with something, it's amazing. You remember it all your life, every little detail. You will remember what you did that particular day and so on, because you invest all of your energy into it. Thought, you know, concentration and so on.
Now, can you say that?
It tells you that the only knowledge is what you do and not what you read, what other people know.
Can you say that since we know that in 1 generation and in 2 generations we cannot have an additional CP phase, and therefore we can say that to remember this result that it should be proportional to n minus 1 to n minus 2 because for n is equal to 1.
Well, I don't know whether it really, that's the only formula that gives, or maybe you're right.
Yeah, we can say that.
Okay, this is Hassan's homework. Okay, he suggests a homework for all of us. Let's try to think of an alternative formula that gives 0 in 1 and 2. It's neat. I've never actually tried that. Maybe you're right.
If we add more points, we can always generate a polynomial. Lagrange interpolation.
Anyway, I don't know, number of phases, in other words, it's 0 for 2 generations. But you remember it all your life, there is just one mixing angle, You remember the Kobayashi-Maskara matrix? I'm sure you don't.
You said field 0 to 0 9. It's just the rotation matrix.
Yeah, but then when you have to work out things, it's hard to see what is going on. When people come my age, they claim that the world was better when we were young. Everything, young people were better behaved, Music was better, movies were better. Actually, my daughter claims that the movies and music of my generation. It's amazing. I find a lot of people that will tell me that the era of 60s, when Beatles and Rolling Stones, all of that emerged, was a great time. I don't know. I don't believe in this nostalgia. It was not true what people tell you. One thing was much better. There were only 2 generations. That, I insist, was a much better world. I was obsessed with having 2 generations. Actually, I had few projects. Actually, we ended up writing important papers with my friends because I would say, well, I can't think of 3 generations. So we will pretend that there are 2 generations. We are working with something in a grand unified theory, and it's very useful to do that. Remember this. Try to do that first, because you may see analytically something. Then people have to struggle numerically later on. But you can, to do numerical studies, it's very good to have a starting point. Otherwise, it's not easy to orient yourself. Why it's also good to think about 2 generations? We are lucky. So when the dust settled, the dust settled, we've learned that we call it theta 1, 2 is roughly theta Kabibo, mixing between the first 2 generations. It's about 13 degrees. Theta 2, 3 is roughly, it's about 10 to the minus 2. And theta 1, 3, actually a few times bigger, maybe like 3, 4 times 10 to the minus 2. So there is almost no mixing. This is very, very useful to us. You can do 2 things when you sometimes just take 2 generations, try to guess what is going on, and the first approximation, just ignore the mixing. You get a good understanding of what is happening, unless you really look for that particular mixing, because especially these, it's a next neighbor thing. You want to interact with your neighbor. Fortunately, you see, 1 and 3, they basically don't interact with each other. The phase by itself is not small. It's about 45 degrees or whatever. I don't remember, we can check it. What we have to talk about, this is the part which is important, but I find it a little boring. You see, I'm not a true phenomenologist, I've noticed. I claim that if you work on phenomena of nature, but I like more the formalism still in me. But we have to talk a little bit about the importance that you've learned. It's me not, but maybe it's good to remind ourselves 2 things. What is really the essence of Kabibo mixing, and the role that the charm plays, and a little bit about CP violation, why we need these 3 generations. Tell me, how do you know that the CP, I don't know, there is not much time. Well, we have still a few minutes. Okay, we have a few minutes. Let's leave 3 generations for when I come back. So so 2 generations I know now look like this. And they really, in the physical basis, there will be d of theta and s of theta, if I write in the physical basis, right? This was in the unphysical basis, where d of theta would be cosine theta d plus sine theta s. and S of theta is minus sine theta d plus cosine theta s. When I ignore the mixing down quark, it's a down quark. This is in the physical basis to tell me that there is. This is equivalent to saying that there is an interaction, U of C, gamma mu. This is of course left-handed. And it looks like cosine theta, sine theta, minus sine theta, cosine theta, cavivo, ds. This is what I mean by mixing. Now notice that I couldn't even talk nicely about this mixing if I didn't have a charm quark. So one often introduces a charm quark the way Jim wrote the paper. It's a sort of strange thing that Jim wrote the paper introducing the charm quark physically as a way of controlling the flavor violation. Notice that I've derived that the Z current and A are flavor diagonal. Today. Trivial. Of course, I assumed that there was a charm quark. Without the charm quark, I wouldn't have been able even to write. None of this would make sense. But we can say a better reason how in the world I can talk about the SU2 cross U1 structure without the charm quark. I need to have a complete doublet. So maybe the better reason to introduce the charm quark is the structure itself. And it's interesting that the idea of charm quark precedes Jim. It's the same Glesher and Bjorken 5 years earlier. So Jim is 69. And Glesher, Bjorken, charm quark is 64. They said that the world would be, they were sort of interesting. There was an aesthetical thing. It would be nicer because leptons come complete families. So we should complete the... But notice what the problem would have been. If I don't have a charm quark, then I don't have this doublet. Imagine that I don't have this doublet. Of course, I don't know what I'm doing. Then notice then I will just have this D quark interacting with down quark. I don't have a charm quark. And notice now that I couldn't claim that there is flavor conservation with the Z boson. Because D bar D bar of theta, D of theta, is D bar D cosine squared theta plus S bar S sine squared theta, right? But there is also D bar S cosine theta sine theta S bar D. So obviously without the charm quark you would have flavor violation. But without the charm quark I wouldn't have the standard model structure. So this is good to stress, but not as fundamental now that you and I know. There is something which is called anomalies that maybe you'll learn a little bit towards the end. Without the charm quark, the standard model would be anomalous. It wouldn't exist. When you have an anomaly, you can't quantize the theory. But that's running ahead of myself.
And we did know about SU2 cross U1 structure from 1961 papers. So why didn't they use this reason to predict charm quark?
Because Glashow, not only that nobody took Glashow seriously, that you can understand. Glashow didn't take Glashow seriously. I'll send you the Bjorken and Glashow paper 1964. They don't cite Glashow. This is mind-boggling.
Bjorken is not a Nobel laureate. The Glashow is.
Well, that can happen when you write something and you're ahead of your time and nobody pays attention. And you can't, well, what can I tell you? You think my monk would remember that he did some painting, he would do thousands of painting, he was drinking on a field and wrote some painting, it would cost $40 million later on. He could get a bloody penny for it. he didn't know that he was creating. Maybe they are not masterpieces, I don't know. But here we know, because this is true. I wrote a paper, I'll tell you when I discussed neutrinos, which was original. I wrote once an original paper in the sense that the next paper in the field appears many years later. Usually when you work with something, it doesn't matter how original it is. Someone else is thinking about it. Maybe from a different angle. No, not seesaw. Other people were doing seesaw. No, unfortunately, no, I wish. There is something else that is important to me. It doesn't matter what it is. I'm embarrassed, nobody paid attention. We were totally ignored. This is with my friend Kyung. And I forgot about it. When I come to seesaw, I'll tell you one of the fathers of seesaw, Minkowski, had forgotten about this paper. I'll tell you about it. We can forget about it. Don't be so surprised, because it's hard to value your work when nobody else does. So, you see, if I have a charm quark, then there is a contribution S theta bar S theta coupled to the Z current. Notice it will cancel this. Right? S theta is minus sine theta D plus cosine theta S. You can see it from here or the way I wrote it. This is equivalent to this. Okay? Up quark couples to this combination, jump quark to this combination. Okay? Please, this is important to see that they are equivalent statements. Note that S theta would be d bar d sine squared theta. You see it? Plus S bar S cosine squared theta. And then we'll have a minus d bar S cosine theta sine theta. Mixing disappears. You can see it explicitly. It's another way of being sure that the Z boson doesn't couple to the mixing, okay? It couples to this linear combination that cancel themselves. Why? Because it goes as U bar U. U bar U adds up to 1. It's not 1, it adds up to 1. I mean, it is 1, but the way it is 1, it adds up to 1, right? Because of the form of the unitary matrices. So we needed the charm quark. So I would say the structure of, now we know better, we shouldn't speak the way Jim spoke. What I want to show you next time that I can relate the mass of the charm quark with KK bar mixing. Let's see for the next. Maybe I can just help me to see how much you remember. You know something about KK bar mixing? What would I look at? How can the charm quark enter there? Just bear with me for 2 minutes so that I can prepare when I come back. What is the KK bar mixing? What do I mean by that?
Are you talking about the theta tau problem?
No. No, talking about KK bar mixing. I have two states, KK bar. Can they be physical states? Why? They go onto each other under CP. They are CP. They are CP sort of transformed into each other. But remember, CP is a good symmetry, basically. Another way of when I tell you the way I speak, when something is small, like neutrino mass, quark mixing, in the first approximation, forget it. That's 0. Unless you are working precisely on that thing. It's very good memory. CP, as you know, is basically unbroken. Or maybe you don't remember. How weak is CP violation compared to CP conservation?
We studied a ratio, but that ratio was 10 to the -3. It actually gave us the...
Right, there is always a dimensionless number that measures the form. In other words, the amplitude that breaks CP is 1,000 times smaller than the one that conserves CP. CP violation is very weak. So basically 0. That means that the physical states must be what we call K plus and minus which is K plus minus K bar, normalized, assuming CP symmetry. Well, it's very little broken, so this is a good approximation. So that means that K bar mix. Right? The states are the mixture of K bar. Do you notice I'm violating strangers by 2 units? You're looking at the clock, I understand that. Time to eat and so on, okay? But it's still an hour and a half. Bear with me because I want to see how much you remember, how much I should cover it. It seems to me, you see that we have to repeat things that we not did.
So you are talking about the definite CP states and the K plus minus states.
Right, CP is a good symmetry.
Yeah.
Forget violation of CP. I'll introduce it when I have to worry about violation of CP. Unlike parity, parity is maximally broken in the world in which we live. You know, it's really a crippled world. But CP is 1,000 times smaller. It's 0 for you and me. I mean, we are doing calculations which even when we do 10%, we are. You know, I'm looking at a W decay ignoring a bottom quark mass, which may be a few percent effect. So that means that they mix, the physical states are the mixture of K bar, but they have opposite strangeness. So it means that strangeness is violated. By how many units? Okay, I'll have to start from scratch. This is strange, this is anti-strange. So how much I've done? By 2 units. I went not from strange to 0, I went from strange to anti-strange. That means I have to get a process in which strange. So the trivial thing would be to do like this. Exchange a Z boson if Z boson coupled to. If you have flavor violation, you will get immediately twice. But there are no such couplings, we found out. So how will I get this? How should charm quark matter? We are talking about down quark system. Which loop?
Up charm loop.
Right, but which loop? What is the loop? Tell me this and I'll let you eat.
You have an.
I'm hungry too, by the way. I'm very hungry.
B going to U.
Sorry?
B going to U and C.
See, no, I'm talking about down quarks. There is nothing about charm. It may be inside the loop, but it cannot be outside. It's like this. You know what? I exchanged Z and I said down quark becoming strange quark twice, let's say. This would change it by 2 units. Seriously, kind of. And not only him. I'm sorry. I love you. What can I do to?
You have an up quark.
Right, right, but what do you want to, which particle tell me up quark? I have up quark because well, the only flavor violation is in a W. So I have to bring in W. Okay, this is what I wanted to remember. And of course W carries charge, so I should bring it twice. It seems to me I have to talk about it, right?
Yeah.
I think it's good. So when I come back, let's talk about it, as if it was not taught. Okay, I can see that the memory is not so strong. So I'll start from scratch.
Actually, Dr. Smirnov discussed the loop, but he discussed the loop for the decay of K to the mu bar, or mu plus mu minus actually.
Not this one.
Not this one. And in that loop,
okay, then I'm sorry, I thought it.
No, in that loop we have up and mu neutrino in the gym mechanism like that. In that loop. And he added an additional diagram where we have charm, and then he talked about mechanism. He just didn't discuss this loop.
Because the charm quark comes from here. Well, anyway, it will be complementary. That comes much later. The charm quark was introduced to predict this to them. Not only that, I will give you the measure of the charm quark mass. Okay, it's good. Anyway, I'm sorry. It tells me that then I was sure you did that. I'll still check with him. It's not that I don't believe you, but it sounds strange to me. Anyway, that's it. We can turn the thing off.